Okay, we're off to chapter 4. This will be exam 2 material, as exam 1's coming up in a couple days here on Wednesday. Again, we're going to take that during lecture time on Wednesday. So in this chapter, we're going to talk about the atom, obviously. We're going to talk about some experiments that led to our understanding of the atom, its structure. As we sort of go through the experiments, obviously we'll talk about obviously what you should know in terms of the experiment, stuff like that. Towards the end, we'll talk about, I believe, protons, electrons, neutrons. I'm trying to remember what's in the chapter. Protons, electrons, and neutrons, and we'll also hit, I think, the periodic table in this chapter as well. So a lot in this little chapter. First, though, we're going to start a little bit about compounds and formulas of compounds. A compound always contains the same relative number of atoms for each element. Just a reminder of a couple of things. First off, right, we have elements. Elements are really the sort of basic unit of everything. They are the basic, an atom is basic unit of each element that's present. There's also molecules. And molecules and compounds are oftentimes confused with each other, or sometimes people think they're always sort of the same thing. And just a reminder that molecules are really a basic definition of two or more atoms together. Now, those two or more atoms could be of the same element. They could also be different elements. So molecules is more like, again, it's sort of that basic definition of all you really need is two or more molecules. Now, there are certain elements that come as diatomic molecules. And those are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. The way that these particular elements come by themselves when they are uncombined is, again, they come as twos, basically, which are what di means, and atomic means two atoms. So basically, hydrogen is two hydrogens, oxygen is two oxygens together, and so forth. So each of these things, in addition to everybody else that you find on the periodic table, they're all elements. But these kind of 7 here are also can be classified as molecules because they do meet the basic definition of a molecule, which again is basically just you just need 2 or more atoms together. Now, a compound, on the other hand, is really a definition of 2 or more atoms of different elements. So 2 or more atoms of different elements is what makes up a compound. So water, as it says there, is basically always kind of 2 hydrogens and 1 oxygen. And thank you. And obviously here we have basically an atom of oxygen and 2 atoms of hydrogen to make that up. We actually drew it, so 1, 2, and 3 atoms together. So something like water, for example, is a compound. It is also a molecule, but it is obviously not an element, as it obviously has more than one element involved in there. And that's like something like H2 is a molecule and an element, but H2 is not a compound because it only contains hydrogen. So again, that is the difference between sort of a molecule and a compound. So when we do write a chemical formula, we do express really the atoms and the number of each atoms using their symbols and a subscript. So in the case there of our H2O, when we do write a subscript, it always goes to the guy to the left of it. So that 2 would mean there's 2 atoms of hydrogen. And much like a lot of chemistry, if we don't write any number there, It actually goes to the guy to the left as well, but it basically means one. And again, we don't usually put the one when we're writing chemical formulas or anything like that. But if you don't see a number next to it, it does imply that it is one of those guys there. Any questions on that there? So when we write formulas, as I mentioned, we use the proper chemical symbol. As you can probably see from the periodic table, chemical symbols are basically one of two ways. They're either a capital letter, and they typically are a capital letter if it is just a one-letter symbol. If it is a two-letter symbol, then it is first letter capitalized, second one not. And that is the rules when you kind of write formulas. So first one capitalized, second one not. If it is a two-letter symbol, all one-letter symbols should always be capitalized. Once again, we do use a subscript down there to indicate how many of each of those atoms we have. As we'll later talk about in a later chapter, they also sometimes represent the moles. But again, here we see the two going to the hydrogen and the one going to the oxygen. Nothing written here for the carbon, so 1 and 2. Nothing written for the nitrogen, so 1 and 3 for the hydrogen as we go there to the left. So that is again what our formula should look like. A reminder as well, writing formulas for symbols, you do want to follow this format. You do not want to write everything in capital letters because, for example, if you did this versus this, that is carbon monoxide. That is the element cobalt. So again, it's really important not to capitalize all the letters there, definitely when you're doing the symbols, because it is, you might be writing something you're not meaning to write in that particular case. Any questions on that there? All right, so for a moment here, why don't you take a second and write the proper formula for each of these descriptions and see what you come up with. Okay, let's take a look. So we're looking for a molecule that contains 6 carbon atoms. So carbon is C, and 6 would go next to it. And 6 hydrogen atoms. Hydrogen is H, and again, we would put a 6 next to it. So that would be our formula there. A compound that contains half as many calcium as chlorine. So calcium is Ca, again, capital C, lowercase a. And chlorine is Cl. And if it contains half the amount of Cl, so I'm going to give Cl2, and then my calcium would be 1, which would be half of 2 in that particular case, also known as calcium chloride in that particular case. Lastly, we got a compound that contains equal numbers of sodium, which is capital N, lowercase a, nitrogen, which is capital N, and 3 times as much oxygen, which is O, so 3 would be there, a little sodium nitrate in that particular case. Any questions on chemical formulas there, how to write them? Yeah.
So like it says like a compound containing half as many calcium atoms as chlorine.
Mhm.
Do you care?
Technically, we'll talk about it. So we'll talk about it in maybe a little later chapter as well. But essentially, the lowest, you usually want to put those guys together, especially when it's a metal and non-metal, which was those two guys are, in the simplest way to get to 0. So if you had, for example, if you had like Ca2 and like Cl4, for example, or something like that. So when you look at these numbers, you can actually reduce them down by 2. And that would get you back to here, which is what you should do in the case of when you put a metal and non-metal together, which we'll talk about in a later chapter as well. Yeah. Other questions? Okay. All right, so now we're going to talk about really the atom itself. And again, like I said, we're going to talk about some experiments that were done along the way to help us really understand, hopefully, sort of what particles are present in an atom, where they're located, and so forth. So everything sort of started a long time ago with the idea that atoms were very small, indivisible type particles. And they were early on sort of named atomos, which means uncuttable or indivisible, kind of unbreakable type of things. Now, a lot of things came to the understanding of what was going on, and they felt that most natural materials were pure substances. Remember, a pure substance is something that is just by itself. It is not in combination with anything else. When we do put substances together, that's what gives us mixtures, as we talked about in that one chapter there earlier on. A pure substance is either an element or a compound. The law of composition means that every compound will always have the same composition of their elements, regardless of where it comes from. So an example, there's always 8 grams of oxygen for every 1 gram of hydrogen in water, and that is because the formula there is H2O. Hydrogen is about 1 gram per mole. Oxygen is about 16 grams per mole, which means since we have 2 hydrogens, that's about 2. 16 divided by 2 is about 8 grams of oxygen for every 1 gram of hydrogen in water. Doesn't matter where you get your water from, it'll always have that same composition. By mass, for example, because it should be made up of the same ratio, if you will, of elements that are present in that particular case. Now, one of the first sort of theories about the atom was one done by Dalton, and this is Dalton's atomic theory. And John Dalton wasn't a very good sort of lecturer, but he did show good talent for math and science in early years. He would always like wake up and kind of record the weather when he did. He never married, but he did like to go bowling on Thursdays, which is obviously a very important piece of information. Show up on every exam, so don't pick any other day. Pick Thursday, not like half price Saturdays or anything like that, right? So it's Thursday. But what he really did was he formulated a precise sort of definition of what we call atoms. And let's talk about some of the main sort of parts of Dalton's atomic theory, which you do need to know. And the idea here of a theory, as we talked about, is it can be sort of proven maybe not correct in all aspects or incorrect as more experiments went on. So there are some parts of sort of Dalton's atomic theory which are not really correct, and there's some that are still correct sort of today. So elements are composed of extremely small particles called atoms. They're really not indestructible, as was earlier thought. That's one of the sort of ideas that is not so true anymore, that sort of atoms are indestructible. Nuclear reactions will basically make that sort of happen. You could basically change one atom into something else. All atoms of a given element are identical. This part as well, in addition to atoms being indestructible, is not correct as well these days, because of later it was found the existence of isotopes. And as we'll talk about, isotopes are basically the same element, but they have different masses. So obviously, if they're the same element, but they have different masses, they are not identical to each other. So there's some type of difference between those types of isotopes. So not known upon actually at the time. Obviously, Dalton did his atomic theory, but later sort of discovered, disproved sort of that part of it. The second part of that sentence, though, is still, or the second part of that is correct, though. So atoms of one element are different from atoms of another. So if you have a copper atom versus, say, a nitrogen atom or a potassium atom, they will have differences in terms of their atoms, in terms of really protons, perhaps electrons, neutrons that make them up. But again, if you have the same element, you also can have some differences, especially in the masses and really in the amount of neutrons that they could have because of those isotopes. Compounds are composed of atoms of one or more elements, as we just talked about. That's what makes something a compound. You got to have the multiple sort of elements involved, not just multiple atoms. A chemical reaction involves only really the separation and recombination of atoms, and that's the idea in a chemical reaction. That's pretty much all that is taking place. As we talked about, I think in the energy chapter, pretty much all you're doing is just breaking bonds, and then you're remaking bonds on the other side of the arrow, if you will. That's all electrons. And that also means that we're just really rearranging atoms. We're not changing any atoms because we're not really dealing with any type of particles that will change what an element is or the element into a different element. The law of conservation of mass means we cannot create nor destroy matter. And the idea also of that is, just a simple one of, we talked about reactants and products. So if you had 6 carbons on your reactant side and you had 6 carbons on your product side, because carbon is about 12 grams, you would have the same mass of carbons on each side. They may just be in different things on opposite sides of the arrow, so those carbons may be mixed out into different compounds on the product side than they are on the reactant side, but ultimately you got 6 carbons on the left, 6 carbons on the right, you will end up with the same mass in terms of the carbon. That's also one of the reasons why when we use an equation, as we'll talk about, we always balance the equation because we should not lose any elements along the way. Or make any new elements along the way in a chemical reaction. Not so true when you get to 1b and you talk about nuclear reactions. That's all you do is basically make new things on the other side of the arrow and stuff like that. But in every day, what we deal with in this class, which is chemical reactions, you do not change elements from one element to the next. We just break everybody apart and they rearrange. Yeah. I just made it up to 6. So I was just saying, the 6 in front of it, as we'll talk about with equations, that's what's known as a coefficient imbalance equation. Basically tells you how many of whatever's behind it you have. Like if it was 6 in front of water, for example, that means you have 6 atoms, basically, or molecules of water in front of it. Yeah, so same with the subscript. The 6 in the front here would be like an imbalance equation. So for example, if you had like 6 waters right on this side, the 6 means you basically have 6 water units, and each of the water units would have the 2 hydrogens that you see in the formula for water and the 1 oxygen. But you would just have 6 of these units basically. And yeah, other questions? So Dalton again pictured compounds as collection of molecules coming together, and you can, as you see there, have basically the same elements involved, but different arrangements, different ways that they are bound together will essentially give you different compounds. They will also give you different sort of formulas for these compounds in this particular case. And if you look at something, for example, if we look at nitrogen, which is about 14 grams, oxygen is about 16 grams. And if we just take the ratio, for example, of oxygen's mass to nitrogen's mass here of 1401, so we take 16 divided by 1401, we end up with something like 1.14 as the ratio, basically oxygen atoms to nitrogen. We take this guy's got, again, for oxygen, 32 grams, as there's basically 2 oxygens involved, each at 16 each, divided by 1 nitrogen in this case, which is 1401. So we do like 32 divided by 1401. You end up with 2.28 as sort of the ratio, right? If I take 2.28 and divide it by 1.14, we equals 2, right? And as we see here, from here to here, there's twice as many oxygens, right? So the ratio here, which is the law of multiple proportions, is the idea that these things come together essentially in whole number ratios. So when we add our atoms together, in terms of their mass and everything, they come together in these sort of whole number ratios. We never have sort of a half an atom or anything like that coming in. It's got to be a full atom. And the ratio of the mass, for example, of one element to the other is a whole number sort of proportion. Any questions on that there? Now let's talk a little bit about the structure of the atom. Now, based on Dalton's atomic theory, there are a few things that were thought of. The atom is, again, the basic unit of any element. It's also the basic unit that could come in chemical combination. And a series of investigations from 1850 to the 20th century prove that although atoms are extremely small sort of entities, they're actually made up of even smaller particles, and these are sometimes referred to as subatomic particles. And as you may know, and as we will talk about, there's three such subatomic particles. There are electrons, which are negatively charged. There are protons, which are positively charged, and there are neutrons, which have no charge. So these are really the three sort of subatomic particles that make up an atom. We have our protons, we have our electrons, and we have our neutrons. And we're going to talk about different experiments that help us understand where these sort of particles end up in the atom and how we sort of figured out that, you know, they're there versus somewhere else, and really sort of the whole sort of nature of the atom. So we're going to look at each of these particles and sort of the experiments that helped us understand it. Really, the electron is the first sort of particle that we looked at. And when we talk about sort of these explorations of the atom and the different parts of it, really radioactive type particles were used a lot. And one of the basic principles of chemistry is the idea of opposites attract. And what that means is something that is positively charged and something that is negatively charged, they are going to be attracted to one another. So much like in life, right, things that people that are too positive don't really want to be around each other, right? There's just too much positivity. Two people are negative don't want to definitely be around each other, but so they say you try to find somebody that balances you out. So you find somebody perhaps positive, a little bit negative, and they attract to one another. So in chemistry, anything with opposite sort of charges will attract each other. Anything that has the same charge will basically repel one another. And that's a really important sort of aspect. And experiments were done that took advantage of this idea, because these particles that they were sort of investigating, protons, electrons, and neutrons, you know, they mainly had charges. So as we will see, there are alpha particles. And alpha particles are positively charged radioactive particles. And they are essentially, as you'll learn in 1B as well, they're essentially the helium nucleus, so they're essentially helium. There's also beta particles, which are negatively charged. I guess negatively charged, I go that way. And we just do the beta symbol, looks something like that. And there are basically gamma rays, which has sort of that symbol there. And they have really no charge associated with them. So they are basically just pure energy. They have no positive or negative charge. So a lot of experiments took advantage of using these and maybe some other sort of radioactive particles to explore the atom and sort of see what's happening. The idea of that, as well, as we will see, and maybe we'll see a picture, I think we will probably a little bit later, but maybe I'll just jump the gun there. If we had something like an electrical field, which is sometimes used as well. So if I had an electrical field, for example, which has a positive side and a negative side, and I shot some type of particle there, and it ended up bending up towards the positive side, that would probably mean that particle has what charge? Yeah, it has a negative charge, right? Opposites attract, so it's going to bend towards the positive side. Same thing if you shot something that kind of bent towards the negative side of the electrical field, that would most likely mean that sort of beam there was more positively charged. And if you shot something that just kind of went straight through, as straight as my bad straight line is there, and it really didn't bend anywhere, then it probably had kind of no charge taking advantage of it. So electrical fields are sometimes used. You can use a magnetic field. It's got a south pole, north pole, kind of works the same way. It'll bend either towards the north or south, depending on what charge it's associated with it. So when we look at the electron, one of the first ways that people sort of looked at it and did investigation of it came about with the cathode ray tube. And the cathode ray tube, which is sometimes abbreviated as CRT, is basically just that idea. It has sort of an electrical field. It has a negatively charged plate on one side. It has a positively charged plate. And it has beams of particles. And these are negatively charged particles. And this beam of negatively charged particle will move away from the negative plate, obviously, and head towards the positive plate. And a lot of times they could put some type of material up here that will fluoresce when the beam hits it so you can actually see it. Now, you might be familiar with the CRT tube. Those are, if you've seen an older TV that has like the big back, not a flat screen or anything like that. Years ago, they used to put TVs on the ground, call it TV repairman. They pop off the back of it. Your picture tube was essentially a CRT tube. Obviously, not these things and stuff like that. Maybe you've seen an old computer monitor as well that kind of comes out in the back like that. That's also a CRT type of monitor and stuff like that, and a CRT tube. And the cathode ray tube, as I mentioned, basically is filled with negatively charged particles like what we assume the electron is. And it has those charged plates, which allows it to kind of flow from the negative side to the positive side, which is known as the anode. As I mentioned before, sometimes it will hit the surface that's coated with some type of material so you can actually see what's going on. And as I drew there a second ago, we could use that advantage of something that has a charge and a magnetic field and an electrical field, for example, to see what happens. So as we talked about before, if it sort of bends towards the negative, or the North Pole, if you will, it's going to be more positive. If it bends there towards the positive side, it's going to be more negative. And obviously, if it just goes straight through, that guy's going to have no charge associated with it. This is a cathode ray tube. We'll see if it plays, maybe.
Ray or Crookes tube. It produces a beam of electrons as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So you can see again, that beam, that the little bright light in the front is the beam of basically electrons negatively charged, and the front would be more positive as it's heading that way. And obviously you can see it is definitely affected by the magnet being there, just like it would be in an electrical field. And again, that's really important for exploring the atom and particles associated with it. So one of the sort of earliest experiments and sort of important experiments that you do need to know in terms of the electron was one that was done by Thomson. And Thomson actually used a CRT, or cathode ray tube, to basically figure out, and as you can see, there he is with his cathode ray tube right there. So you can see that he was able to figure out the charge to mass ratio of an electron. So Thomson was able to figure out this charge to mass ratio of an electron, and that happens to be the number there, minus 1.76 times 10 to the 8. The big C is a coulomb. That is a unit of electrical charge per gram. So coulomb being charge and grams being mass. So this is one of the earliest and important sort of experiments that helped us understand sort of the charge to mass of an electron. And this was an important step in understanding about electrons. And with that, another really important step in terms of electrons was one done by Millikan. And Millikan did an experiment which is known as the oil drop experiment. And essentially, that's the setup there on the right and also the left there. Basically, in the oil drop experiment, it had an electrical field. And what he would do was shoot some oil droplets in. The droplets would start to fall through the hole as they were atomized, and it would start to drop by the force of gravity. What he was able to do is actually adjust the electrical field in such a way that basically he was able to suspend the oil droplet in the air. It wouldn't fall, it wouldn't go up, it wouldn't go down. He was able to kind of dial it in. And that's because as the oil droplets were falling, they gained a charge. And now as that thing has a charge, he's able to use the electrical field really to sort of dial it in and figure out really the magnitude of a charge of an electron. And that's what Millikan essentially did, is he was able to figure out the charge of an electron, which is this number right here, minus 1.6 times 10 to the minus 19. And here's that little animation of it. He was able to adjust that little electrical field and essentially just kind of float that oil droplet and have the charge associated with it. Now, why that's important, if you take sort of the experiment that was done by Millikan and the one that was done by Thomson, if you put those together where we had basically the charge of the electron done by Millikan, which you need to know, and we had the charge to mass of an electron done by Thomson, if you put those guys together correctly mathematically, you'll actually get the mass of an electron. And the mass of an electron is 9.09 times 10 to the minus 28 grams. Probably a number you perhaps should know because it does pop up a lot. Is that a large number or a small number? It is a small number, right? It's like 27 places to the left there and adds zeros. Those are really small mass. So in terms of our electron, a lot of discovery in terms of the electron and its properties were done using CRT tubes, the cathode ray tubes. Thomson using it to get the charge to mass. Millikan doing this oil drop experiment to figure out the charge. Putting those together allows you to figure out the mass of an electron. Any questions on that there? Now that we have some information about the electron, the next thing we're going to talk about is the proton and the nucleus. So at this point in the early 1900s, a couple of things were really thought of. And it was this idea, obviously, through the experiments of people like Thomson and Millikan, that atoms definitely contained electrons. They were also thought to be atoms electrically neutral, which means if they're going to be neutral, but for sure we know they contain these negatively charged particles, that means somewhere they have to contain something that's positively charged to balance out the negative charge from those electrons. Around the turn of the last century there, the accepted model for the atom was one that was proposed by Thomson, different Thomson actually, but Thomson as well was his name. And the atom was thought of as being this sphere of positive charge. So this kind of circle, and throughout this circle, it had all of the positive charge basically spread out. And in addition to having all this positive charge basically spread out all over the atom, it had these negative particles locked in or sort of in there. And these negative guys are our electrons. So this is what is sometimes referred to as the plum pudding model of the atom. And that's like a dessert kind of pudding with raisins dropped in like electrons, basically. So you have this positive charge spread all out through the atom, electrons embedded inside this positive charge, kind of like raisins in the pudding. And this was sort of the accepted model, and here's a much better picture of it. Again, all that blue is positive charge, electrons sort of embedded inside. The other major idea of this model of the atom was most of the mass of the atom was the electrons. So it was believed at this point that most of the mass of the atom was the electrons. And again, like I said, this was sort of an accepted model of the atom until obviously further experiments came along. And really the next major sort of experiment that allowed us to understand the atom was one that was done by Rutherford and some other guys like Geiger and Marsden. And this is what is referred to as the gold foil experiment. And the gold foil experiment is one where they shot these alpha particles at pieces of gold foil and other metals, and they wanted to see what happened. So these alpha particles, which again are these positively charged radioactive particles, they're moving really fast. So the idea of what they thought was going to happen in this case was, for example, if we use our plum pudding model here, which is what they thought the atom looked like, they thought because they were shooting these alpha particles, which are positively charged, they should go through with a little bit of deflection. And the idea is, for example, if this was, say, the atom and this was all the positive charge, and if I held, for example, one end and somebody else held the other end, and we shot like a pen or something at it, right, really hard, right? It probably would be able to pop through the other side, right? But it would kind of deflect a little bit as it kind of popped through, as all that positive charge is spread out. So even though they're going to be repelled by one another, it's not really a thick sort of layer, if you will, of positive charge. It's really spread out. So these things are heavy and moving really fast. They'll be able to kind of punch through it with a little bit of deflection as they went through. And when they actually did this experiment, they were quite surprised because, frankly, that is not what they saw happen. What they saw happen when they did this experiment was essentially these alpha particles did not have much of a problem. They just basically sailed right through. But they did notice that although a majority of these alpha particles sailed right through, every so often they would see these alpha particles bounce off at these really large angles. Sometimes they would even head back to sort of the source of the alpha particles. And that was a really important sort of discovery, because if most of the alpha particles went through with no deflection, that means they most likely ran into what? They most likely ran into nothing, right? So if I threw my pen, for example, and there's no paper there, right? My pen's going to pretty much just sail straight through. Nothing's going to get in its way. Nothing's going to happen to them, right? But in this case, they did see every so often that these alpha particles did bounce off at really large angles. That would mean that the alpha particles had to hit something that was what type of charge to bounce off at that really large angle? Not negative, because it would be attracted, right? So it would just stick, right? So it has to be something that's very, very densely positive, right? So it had to hit something that wasn't just kind of positively spread out, right? It had to hit something that was pretty packed in there, pretty tight, with a lot of positive charge. And that would account, for example, why we see these things bounce off at really large angles. So we go back to the example, I won't do it, but if I took my paper and instead, right, really folded it a whole bunch of times, instead of my positive charge being all spread out in the entire part of the paper, I end up with, like, super small amount of paper, right, folded down. All that positive charge is going to be basically in one location, and it's going to, now if I try to throw a pen through it, right, it's going to bounce right off of it. It really won't go through. So let's take a look at that here.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electron. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle. In 19...
So again, you see here a little setup of the experiment, which obviously you do need to know. And you do need to know what they sort of expected to happen, which again is they expected most of them to go through with a little bit of deflection. You also need to know, obviously, what they did find, as we've been talking about, that most went through undeflected, as you can see here on the screen. But every so often, we did get some alpha particles being kind of bounced off at these sort of large angles. So as I mentioned, they sort of compared it to like shooting a gun at a piece of paper and having kind of the bullet come back. Again, it had to hit something that was super, super densely positively charged in order to cause that very fast moving, kind of heavy alpha particles to be bounced off at that really large angles. So on the left there, sort of what they thought they'd be able to kind of punch in based on the plum pudding model. Over here on the right, sort of more what they saw. And what this meant was they had to sort of abandon, if you will, the plum pudding model. So they kind of had to go back and go, well, that was a nice early sort of definition of the atom. But based on the results of this experiment, it is not so true. And basically what they found is, as it says there, that the atom was mostly empty space. And that is really what accounts for those alpha particles going right through with no problem. They also said that it had to contain something which they called a nucleus, which was a very positively charged, dense core. And one of the last differences between sort of the modern version of the atom and the plum pudding model of the atom is that most of the mass of the atom is the nucleus. So unlike the plum pudding, where they said most of the mass of the atom was the electron, actually based on sort of this experiment and future experiments as well, it was found that it's mostly the nucleus that is most of the mass of the atom. As we'll learn from future experiments, that is where we find our positively charged protons. And later on in like 1930s, neutrons are found in the nucleus as well. So later our experiments found the location of those guys being in the nucleus, and protons, which are positively charged particles, being there makes sense because, again, that is pretty much what's going to make those alpha particles bounce off at large angles, that very densely positive core of an atom. Where are the electrons? The electrons are essentially, we have our protons, right? And our neutrons in the nucleus. Our electrons are randomly traveling in that empty space around the nucleus. By the way, as we'll talk about, electrons don't travel in pretty circles or anything like that. They travel pretty randomly about the nucleus. Is there going to be an attraction between electrons, which are negatively charged, and the nucleus, which is ultimately positively charged? There is going to be attraction. That's why all your electrons just don't fly away, right? So there's electrons are negatively charged, even though they're flying around randomly in that empty space. There is an attractive force between those electrons and the nucleus. It also accounts, as we'll talk about in later chapters as well, why certain electrons, for example, are involved in bonding and other electrons aren't. And the outer electrons, which are further away from the nucleus, are the ones who are involved in bonding typically because they're not held as tightly. One of the things about sort of the electrostatic attraction, which is sort of the positive negative attraction between things, is it does increase with strength or size of that sort of charges. So for example, something with a +1 and -1 charge will be attracted to each other, but something, for example, with a +3 charge and a -3 charge would be much strongerly attracted to one another because the charge is larger. So as those sort of charges increases, the attraction between the positive charge and negative charge is a lot stronger than, say, you have the same sort of positive negative charge with a lower overall value, if you will. It's not going to be as strong of an attraction, but they will be attracted to each other nonetheless. So you do need to know, obviously, Rutherford, like I said, what was done in the experiment. You need to know what they thought would happen, what actually did happen. You need to know the modern version there of the atom, how it is similar and different, obviously, are different comparison to the plum pudding model. Any questions on that there? All right, so here's just a table of some of the experiments we talked about, sort of the outcomes of those experiments, and it kind of covers all the stuff we just talked about there, from Thomson and the cathode ray tube to Millikan to Rutherford, and obviously earlier on we talked about Dalton's atomic theory, which you need to know as well. Now we talked about protons, and protons again were found to be positively charged. They're also been found to be in the nucleus of an atom. They have a mass of 1.67252 times 10 to the minus 24 grams. If you remember, the electron was approximately 9.09 times 10 to the minus 28 grams, give or take. And that means that the proton is actually much, much heavier than an electron. So by the way, when you compare numbers that have negative exponents, a reminder that the negative exponent that is smaller is actually the larger number overall, because minus 24 means only 24 places to the left. Minus 28 is 27 places or so there, or 28 places to the left there, and add some zeros. So on average, a proton is about 1,840 times heavier than any electron flying around. That also sort of reinforces the idea that came out of Rutherford's experiment that most of the mass of the atom is made up of the nucleus, because in the nucleus you have protons, and every proton that's in there is 1,800 or so times heavier than any electron that's flying around it. So again, most of the mass of the atom really is sort of the nucleus there. At this stage, we sort of perceive the atom as the nucleus is really small compared to the overall size of the atom, but it is the most massive because it does have those protons and later, obviously, the neutrons in it. The atom you could think of is, since this is related to the Super Bowl, I suppose, that happened yesterday, the size of the Superdome there. Where they played the football game, and like the nucleus is a small marble, like on the 50-yard line there in the middle, and that's sort of the idea there. Protons are confined to the nucleus, while again electrons are spread out in really that empty space, sometimes referred to as electron cloud, around the nucleus. Again, they are traveling in sort of a random motion, as we'll talk about. A particle like an electron, you really don't know at any given point in time exactly how it's traveling or where it's located. And really the idea is the more you know about, say, how it's traveling, the less you know about its actual location, and vice versa. The more you know about its location, the less you know how it's traveling. That is what is sometimes referred to as the Heisenberg uncertainty principle, is the idea that particles, you don't really know that there's some uncertainty in their path and also in sort of where they're located. And electrons sort of follow that, which again is why they do not travel in pretty low orbits around the nucleus. Now, the neutron, it was always believed that there was some other sort of particle that was in the nucleus of an atom. And it wasn't until about 1932 that James Chadwick basically did some experiments. He did a lot of experiments that resembled basically gamma rays being emitted. And if you remember, gamma rays, again, are pure energy, no charge associated with it. Later experiments show that these rays did consist of neutrally charged particles, and they are called neutrons. they have a mass of 1.67495 times 10 to the minus 24. That also is about 1,800 times heavier than any electron traveling around. And it is found in the nucleus. That also, again, reinforces the idea, as we've been talking about, that in the nucleus we have protons and neutrons. Each of those things are individually 1,800 or so times heavier than any electron. And that makes sense that then again, the mass, most of the mass of the atom is the nucleus that contains those two types of particles. Now, when we talk about this number and why it goes out so far, it goes out so far because it essentially slightly beats the proton in terms of mass. So actually the heaviest sort of particle is the neutron, followed really closely by the proton. Then way down here to the lightest is the electron. Yeah, again, about 1,800 times as less massive than a neutron or a proton, basically. So you do need to know in terms of protons, neutrons, and electrons. I would say probably the electron mass is probably the one that you maybe should know. It does come up a lot. But you do need to know which one is the most massive and which one is the lightest. So again, neutron being the heaviest and a electron being the lightest. And here's sort of the difference, and you can see they're super close, the proton and neutron. But again, the neutron just slightly edging it out in terms of calculations. Here's sort of a diagram of what the atom sort of looks like. Again, you can see the nucleus is very small in terms of the atom size. All this sort of pink sort of color is the empty space, or electron cloud is sometimes referred to. And sort of shows up a little bit up there on the screen. Kind of the darker pink color means there's probably a greater chance of finding an electron in that area. It's a greater electron density, if you will. And as you sort of fade out, it kind of gets lighter pink. And that means there's not as much electrons kind of hanging out there on the edges, but there's a good chance you can still find one. We do see most of the dark color near the nucleus, which again makes sense in terms of that opposite attraction. So there's, if you had to try to find a spot in the atom where you would expect an electron to be near the nucleus, you should definitely be able to find some. As you sort of travel out from the nucleus at some distances, the probability and chance might go down in terms of finding electrons. Any questions on that there? Any question on the atom experiments? Okay. Yeah. Which one's the heaviest? Which one's the lightest of those three particles? Yeah. Yep. Other questions? All right. So the chemistry of atoms, as I mentioned before, and normal chemical reactions come from really breaking bonds and making bonds. And that is pretty much all about electrons. So if you think about sort of the diagram we just saw of the atom, which is essentially this and this, and you have electrons on the outside flying around, it does make sense that when atoms come together, pretty much the electrons are going to be the first ones to see each other and interact with each other, since they're on the outside, basically, right, flying around. And that's pretty much when all chemical reactions involve. So all chemical reactions involve pretty much just that. Breaking bonds, making bonds, that's all electrons. That is also why, as we'll talk about, we have conservation of our elements, because we don't get into the nucleus and change any of those particles in a normal chemical reaction. And that means that we really don't change the elements because we don't get into that nucleus. You could play around with the electrons as much as you want, it won't change the element. But when you start playing with those particles that are inside the nucleus, that is when we start to see basically elements can change. That only happens, as I mentioned before, as in nuclear reactions. Nuclear reactions is pretty much all about that, all about changing what's in the nucleus, while chemical reactions are all about bonds, electrons, making and breaking bonds. So that brings us to some properties of atoms, the atomic number, mass number, and isotopes. So let's talk a little bit about these things. The first one we're going to talk about is the atomic number. And the atomic number is sometimes abbreviated as a Z. And the atomic number's definition is the number of protons that you'll find in the nucleus of an atom for a particular element. Now, one of the nice things about knowing the atomic number, which is also knowing the number of protons, is if you have a neutral atom, and since we know from our conversation a second ago, pretty much atoms have protons, which are positively charged, electrons, which are negatively charged, and neutrons that have no charge. If you know the atomic number, which is the protons, and the thing has to be neutral, and it is a neutral atom, you will then also know how many electrons it has, right? Because it has to have the same number of electrons to balance out the charge to 0. Neutrons doesn't matter because it has no charge, so it can't affect the charge of it. It is also really important, though, to remember that if you're asked a question of what is the definition of the atomic number, the definition of the atomic number is just protons. Okay, so the definition, if you're asked just straight up, what is the definition of atomic number? It is the number of protons only. But if you're dealing with something that is neutral, it will also tell you electrons. But that is not the definition of what the atomic number means. So where can you find the atomic number? Well, you could go to your friend, the periodic table. And it is that number that is typically written above the symbol on the periodic table. That is the number of protons and also the atomic number. So if we look at our friend lithium, it has a 3 up there. And that 3 means that lithium has 3 protons, which means if I have a neutral lithium atom, I should have how many electrons? So I have a matching set of electrons, which are negative. 3 protons, 3 electrons, 3 positives, 3 negatives, gives the guy an overall charge of 0. So every single element up there has an atomic number. If you look at the periodic table, do any of the top numbers repeat? Are they all different numbers on top? They are all different numbers on top. And that's really important because if you know the atomic number, or you know the number of protons, which is essentially the same thing, you know exactly what element you're talking about. So again, if we look here at fluorine or nitrogen up there on the periodic table is number 7. Which means, as we see down here, it has 7 protons and would have 7 electrons to match it. I would never find a nitrogen atom that has 6 protons, right? Because the one with 6 protons is which element? It is carbon, yeah. So it would be carbon in this case. So if you know protons are the atomic number, which like I said before is the same, you will know exactly what element you are dealing with. This is why the atomic number and the number of protons is the most important number, because if you know the number of protons, you know what element it is, and the only way to change the element is you have to change the number of protons. Yeah? So if you do something and the protons stay the same, then you have the same element. And that is why in chemical reactions I was just talking about, we don't do anything in the nucleus. We don't touch the protons or the neutrons. We only touch electrons. And since we're not touching anything in the nucleus like protons, if we started with 6 carbons like that example I did a while back, we should end with 6 carbons because we're not changing any of carbon's protons, which means they remain carbons all through the reaction. They just end up in different locations attached to different things. Any questions on that there? Yeah. Most things, first off, a good question. Everything on the periodic table, if you have anybody on the periodic table that's by itself, it is not combined with anything else. They don't have charges. Yeah. Sometimes people think when we start learning about charges and charges that these elements typically get, they think that the elements always have charges, and that's not the case. So for example, if you had hydrogen by itself, no charge. If you had like a piece of copper metal by itself, it has no charge. So elements that are uncombined basically have no charge. The more simpler answer to that, and more the way that you would see it, for example, is if you see nitrogen written or any element symbol, and there's nothing written to the top right of it, that means it has no charge. You could assume that it is neutral. Or if you have something in kind of writing where it doesn't mention a charge of something, then you could pretty much safely assume that it has no charge, that it is neutral. Things only get charges, as we'll talk about a little bit later on in this chapter, but you will see it in terms of the formula top right. Is usually where it's written. You'll see a plus charge, a +2 charge, -3 charge, stuff like that. So it's usually safe to assume that it has no charge unless it's sort of, you have some type of information that tells you it has some type of charge. Now, again, that's also a really important thing to remember what I just said, which is things just straight off the periodic table, elements by themselves don't have charges. So people always think they have those type of charges. Now, the mass number is also a really important sort of number. And the mass number is sometimes abbreviated with an A. And the mass number is the total number of protons and neutrons that you have in the atom of an element. Now, except for hydrogen, and hydrogen is unusual, which is why hydrogen is kind of upper left there of the periodic table. Older periodic tables, you actually used to put hydrogen on both sides, left and right there, but hydrogen has some unusual sort of properties. Hydrogen has only a proton and an electron. It does not have a neutron. So hydrogen is the only element that does not have neutrons. All the other elements have all three of those particles, protons, electrons, and neutrons. The mass number, which is the protons and neutrons that are present, is really important because if you take the mass number, which is basically the number of protons plus the number of neutrons, and you take the atomic number that we just talked about a second ago, which is the number of protons, and if you subtract those two things, the protons will cancel, and that will give you your number of neutrons. So if you take the mass number minus the atomic number, that is how you could figure out how many neutrons an atom has. When you calculate those things, the mass number, the atomic number, the number of protons, electrons, and neutrons, they all have to be positive whole numbers. So they all have to be positive whole numbers. So if we look at something like, say, hydrogen on the periodic table, 1, and it says something like 1.008. We know that the atomic number is up on top. Can I find the mass number on the bottom? Is that the mass number? The answer is it is not the mass number. So the mass number is not on the periodic table. This is, as we will talk about, what is known as the atomic mass, which is different than the mass number. What confuses people sometimes is the atomic mass and the mass number in some cases are numbers that are very close to one another. So people think, oh, they must have just rounded or something, right? So one of the ways you can remember that is pretty simple. It's the very last sentence there. When you do the mass number, atomic number, protons, electrons, and neutrons, they all need to be what type of number? They all need to be positive whole numbers. If you look at the periodic table, all the numbers underneath the element, for the most part, they're all like decimals. Yeah, there's no whole numbers up there. So none of those are the mass number. You could only find the atomic number up there on the periodic table. Any questions on that there? All right, we're going to